Morning, everybody, and welcome to the Matrix webinar for May 2nd. Today we're lucky to have Kyle Wilsey, a sales engineer at Morningstar, who will present inverters and solar controllers to us from Philadelphia. So welcome, everybody. Thank you for joining us. Kyle, the floor is yours, my friend.
All right. Thanks, Sean. Thanks, everyone. Appreciate you all joining in today. I think we have about an hour, and hopefully I can cover the majority of the material I'd like to in that time. If we want, we can feel free to chime in and ask questions as we go, or we can wait till the end and cover them then. I'll hope to leave at least 10 minutes to get to your questions. Today I just want to cover a bit about Morningstar as a company, dive into the differences in our controller line, down from our smallest 4 amp controllers all the way up to our highest end 60 amp MPPT TriStar controllers, and give you a bit of a checklist to go through as you decide how best to choose a controller for your system, for your off-grid battery-based systems. I'll dive in here to the slides to get started. Hopefully many of you know Morningstar well. For those of you who don't, I'll just maybe take 2 or 3 minutes and give you a quick overview of kind of our history, where we've been, and where we do business. We've sold well over 2 million charge controllers and inverters at this point in time. We have over 230 distributors in 89 countries at last count. In fact, this slide is a bit dated as of yesterday. We did a recount. We've added quite a few countries to our distribution list. In fact, we've shipped product to all 7 continents, and over 111 countries is officially the total. Our mission as a company is first and foremost to produce high quality, highly reliable off-grid solar charge controllers for the world's consumption. We've been in business for 20 years. In fact, this year we've celebrated our 20th anniversary as of last month, and I'm here to hopefully carry us into the next 20. Innovation is a big part of what we do. We have a team of engineers, including several PhDs. We hold many patents, as I'll explain later, and we truly strive to make the best and most highly reliable charge controllers on the market. Charging batteries can be a complicated business, and it requires a equally complex system to manage the charging and provide current to your off-grid loads. We typically expect in a given system, typically in the industry, 25 years or so of panel life at their rated output. And we try to design, well, we can't quite meet that in power electronics. We estimate roughly the charge controller should last at least about half that. So all of our products are designed to a 15-year service life at minimum, and being in business as long as we have, we've seen quite a few ProStars, especially being the first product we released, still out there and working fine so many years later. Customer focus is also a big part of what we do. This isn't just a bullet on a slide. We really strive every day to provide excellent customer support in terms of technical support, marketing support for our distributors and dealers, and continue to focus on this as we develop new products. I'll say that the same engineers who design a lot of our products provide the support, and that's an important differentiator when you're looking for technical questions after the sale, or even beforehand when you're deciding which product is best for you. Won't spend too much time on these, but I just wanted to tell you that we've had a long history. Founded in '93, we introduced our first ProStar in 1995. A couple of years later, issued our first and one of our most important patents on PWM switching back in 1997, which continues to serve as a foundation of many of our products. All the way up through 2003, almost 10 years ago now, we introduced our first 3-function TriStar controller that continues to serve markets very well today. In 2004, we received another patent that's pretty ingenious. Really has helped allow our products to continue to be passively cooled. It's a way that our fast switching mechanisms reduce heat dissipation in our circuitry. That's fed into a lot of the other products you see here, all the way up to back in 2008, our first MPPT solar controller with TrackStar technology, followed quickly by the TriStar MPPT. Coming up in 2013, not shown here, but very soon we expect to release the newest MPPT TriStar, which will handle up to 600 volts on the solar side for typically grid tie strings. And that's a pretty unique product that we're excited about. Expect to see that later this year. So again, just a few points about the company. I wanted to emphasize that we've been in business 20 years. We design our products for roughly a 15-year operating life, hopefully longer. All of our products come with a 5-year warranty, with the exception of the one smaller off-grid inverter and some of our rural type developing nation controllers, the SHS. The rest of our products are all fully 5-year warranted, and we pride ourselves in keeping the warranty and RMA process fairly hassle-free. All of our documentation is multilingual: French, English, other languages. We do business, as I said, in several countries around the world and need to support all languages. Everything that we produce that you find online, data sheets, catalogs, these are all types of marketing materials that we provide to our distributors and dealers as well for promotion of Morningstar. So in general, we really try to be in tune with customers' peripheral needs around the controller, support, marketing, and such. Hopefully most of you are familiar with the general line of Morningstar's products. We offer a range of PWM type solar charge controllers, namely the SunSavers, Sunlight, ProStar, and TriStar, as well as the SunSaver MPPT and TriStar MPPT 45 and 60 amp. All of these controllers, in one way or another, are highly certified. We take a lot of care before release to go through the necessary steps to attain the relevant certifications for these products to go into residential or industrial systems. Not all products are certified the same, and that's due to the difference in their expected market application. But our products are the North American market. You can see the CSA cert is available in the higher end products, as well as the SunSavers. UL, CE, these are all typical certifications that we don't spare. So you can be confident that as you're using Morningstar, it's going to comply with the relevant codes and such that are necessary in off-grid applications. Not a lot of imported charge controllers can claim this. They often don't. They're either not aware or simply don't go to the expense and time to make sure that the North American, Canadian certifications are included in their products. So that's something to watch out for, when comparing Morningstar versus others. Now getting into some of the meat of our product line. I mean, the secrets and to the reliability and the quality really comes into play here with a lot of the innovations that we put great time and effort into building into our products. Obviously, working in off-grid, we need our controllers to be environmentally ready to take what weather and climate will throw at them. So you'll see for all of our controllers, they operate in a wide range of operating temperatures, down to negative 40 C and up to usually 60 C. A few of our products do derate after 45, but I believe that's relegated to to some of the much smaller units. But the TriStars, the sun savers, anything that would be used in a high duty cycle type environments rated up to 60 C. Tropicalization is another issue that is central to power electronics design in terms of reliability. We use a DuPont Humiseal conformal coating for all of our circuit boards. And what this does is it protects against the corrosive effects of salt in tropical environments and high humidity. Realizing many of your systems are up in Canada, the tropical protection isn't so important, but the humidity is going to play a part no matter where you are. And this conformal coating of our circuit boards works to seal out the moisture that can create premature failures in a lot of lower-end, lower-cost controllers that spare this expense. With our SunSaver line and parts of the TriStar and TriStar MPPTs, we also use a proprietary blend of epoxy to encapsulate the circuitry to protect it against many of the elements that would otherwise damage and render useless the charge controller. It's a two-part epoxy resin that protects, in the case of the SunSaver, the entire circuit board. It's potted in this encapsulation. In the case of the MPPT, we use this to seal the inductors in a special well inside the aluminum casting to help with heat conduction away from the power electronics and protect them from the effects of moisture in the environment. You'll also see that the terminals on all of our controllers are plated to protect against corrosion, which can cause all kinds of unwanted failures, sparks, loss of power, and such. With any off-grid system, lightning protection is also a major consideration that must be taken into account, both at the device level and at the system level. So at the device level, we use a transient voltage suppressor to protect the circuitry against near lightning strikes. No amount of internal protection is going to fully protect against a direct strike or a very near lightning strike, but we include these transient voltage suppressors into our circuitry to ensure that if there is some kind of induced voltage, some high induced voltage due to a near strike, that the controller won't smoke and blow up. Again, it's not an end-all be-all solution. You should always use a system, like a full system level lightning suppressor. As you can see here in this image of a weather station in Norway, dual TriStars are in use, and some pretty clear lightning protection built into that system. So together, between what's built in internally and the system level, we feel you can be confident that the solar power electronics for your particular application are well protected. When we start to talk about the robust thermal design, the mechanical side, and some of the specifics of the circuitry, you really can see where the advanced engineering we put into our products comes into play in the form of extensive electronic protections, things like short circuit, reverse polarity, overcurrent protection. It's really difficult to damage a Morningstar controller with incorrect wiring. Changes in the system. It's difficult to do. It's difficult to build into the product, but we feel it's important to keep our systems running in remote, unintended places where they can't necessarily be reset very easily. On the mechanical side, something that definitely sets apart Morningstar from many others is the fact that we insist religiously on keeping fans out of our products. For one thing, it reduces the internal consumption, the self-consumption of the product, but it also makes it more reliable. It's one less part that we have to worry about breaking down or replacing, and we do this with some pretty advanced thermal analysis and some major, as you probably are familiar with in our TriStar products, some big heat sinks. But the design of those heat sinks and the fact that they're able to dissipate heat throughout this power conversion process is pretty important. With a fan in the system, it tends to shorten the power electronics lifetime and cause other issues as well. So the passive nature of our products, all the way up through even our new 600-volt TriStar, is pretty important. We use dual-layer PCBs, circuit boards. This is a bit more of an advanced manufacturing space and also helps with heat dissipation. And we spend a lot of time and effort and money, frankly, testing extensively during the design process at the factory with burn-in periods in order to make sure that whatever reaches your door is as highly reliable as it can be. Here we're just seeing some of the design work that goes into the heatsink on the TriStar. You can see the switches, the FET switches on the underside in red, with the heat being dissipated from them as the main generator of heat in the system, reducing the operating temperature of the system and keeping it running. With a fan, this is sometimes possible, but definitely not as efficient. Not to mention the air and dust and debris that can get into the internal compartments of an electronic product. Usually not a good thing. I won't spend too much time talking about communications. This is an in-depth topic that can go on for quite a while. It's almost its own webinar in itself. But just to give you a quick overview. Morningstar believes in an open standard for our communication protocols. A lot of companies will use some kind of proprietary communication protocol that requires additional equipment and specific knowledge of their particular protocols, but we use a standard Modbus. It's an industrial standard, increasingly used, especially in the solar industry. With some of the SunSpec, I don't know if you've heard of SunSpec work that's going on to standardize communication amongst equipment in solar. And in our higher-end TriStar 60 MPPT with Ethernet, we use a standard TCP/IP internet-based protocol. Makes things easy, makes integration easy, and it enables third parties to develop their own interfaces for our products to monitor variables, voltages, kilowatt-hour counters, and such, to interface with our products without the need for specialty equipment and highly specialized knowledge. So that roughly covers the kind of a general overview of the product side, the advantages of the product side of Morningstar. Now I just want to talk in general about solar charge controllers, what it does and why it's important to spend some time really scrutinizing the choice of which to use in your system. There's a lot of different choices out there. Going back to some of the older technologies, shunt type controllers were common maybe 10, 15 years ago. Still see them sometimes today, but they're often hard on a battery. And the series type. All of our non-MPPT controllers, the PWM TriStars, SunSavers, are of this series type that directly transfer current from the array to the battery. There's different ways to accomplish this via different switching methods. Some are simple on-off to allow the current to flow to the battery. All of ours use a PWM pulse width modulation type that accurately and precisely delivers just the right amount of current to the battery for optimal charging. All the way up to probably the most complicated type of charge controller, the most complex and often more expensive, MPPT. I'll talk a little bit about how these different types interact with battery systems and what considerations you need to make when making that decision. So again, I hope it's fairly well known. The primary purpose of your charge controller is to prevent the solar panel from overcharging the battery. also prevent it from undercharging the battery. We want to harvest as much as we can from the panel while the sun is shining, and maintain those batteries at the highest state of charge possible. Keeping the batteries charged at a high level is good for batteries. Every battery manufacturer will tell you that it will increase battery life the higher the state of charge you can keep over time. Load management is also a consideration that we've included into many of our products. The ProStar, SunSavers, the TriStar PWM type controller can also be used as a load controller. This is why we typically design an off-grid system to run loads. So with the charge controller as kind of a central point in the system, why not use it to help manage loads, cut them off if battery voltage gets low to prevent over discharge and things of this nature. You also want a charge controller to tell you what's happening with the system, either through a simple set of LEDs. A lot of our products have a simple green, yellow, red type LED. ProStar and TriStar, our SunSaver Duo, they are available with additional meters that can give you quite a bit of high-quality data about what's happening in the system. And again, the charge controller will facilitate the remote communications with the rest of the power system. So here it is kind of as a central point of the system, and this is really how we feel off-grid system design should be viewed, with the controller kind of as the central brain to the overall system. It's a tie-in point for your panels. Maybe you have an auxiliary generator. Definitely your batteries for some of the, maybe a residential backup system. You have your inverter charger that runs your AC loads. You may have DC loads. So you can see it. The overall system can get pretty complicated pretty fast. And without something in the middle to manage the overall functioning of the system, you're often left with lots of questions about what's happening. So the controller with a meter, with LED indications, load terminals, clearly marked PV terminals, when it's installed, should be able to give you an easy access point to both install and troubleshoot if need be later on. Going back to the primary purpose of the controller, I hope this is again a familiar image to most of you, but battery charging. This is the primary function that we spent quite a bit of time and effort perfecting over the years, a PWM type 4-stage battery charging algorithm, again standard in all of our products. Typically through a charge cycle, one day, your batteries might be depleted over the course of the evening. At the morning, when the sun's coming up, the controller should be allowing in a full charge to the battery. Almost as much current as can be produced by the array, maybe limited in some cases, but generally a wide open circuit that allows for a full charge. Once the battery voltage reaches a certain set point, we move into regulation, and slowly over time start to taper the current down to a level that equates with a high state of charge of the battery. And once it's fully charged, it's reached its voltage regulation set point, we drop it into kind of a float mode that just maintains that battery charge at a bit of a lower voltage level to be ready for use later when the loads need to come on. There's also an equalized stage for certain types of flooded batteries that need a bit of a boost periodically to even cell voltages and prevent corrosion on the internal lead plates of the batteries. This is kind of a general overview. There's a lot more to this, but in general, most of our all of our PWM controllers use this algorithm to maintain batteries, which, let's face it, are a pretty expensive part of the system, and properly maintained with a controller like this, they should last quite a long time, well over 5 years, some 10 and more. As I mentioned, shunt controllers used to be a bit more prevalent. This is kind of a thing of the past in many ways, but we do see a few of these in oil and gas type applications, where basically your controller just shunts current from the battery through the controller in order to reduce charging current. It's kind of a real rough way to charge a battery. We actually don't produce and have never produced a controller that uses this, so I'll just move into the series type. The series type charge control puts the controller directly in line, as I mentioned before, between your array and your battery and or your load, and uses a voltage sense device in between to precisely measure the state of the battery and divert current through to recharge it as the load draws it down. The switching that you see on the top here, labeled as HVD and LVD, is what varies in different controller designs. The manner of the switching, the type of switching, but this is what the primary function of the controller is doing, regardless of what controller you're using or which brand controller you're using. Last notes on the PWM type regulation. The primary function of this type of controller is to measure accurately the battery voltage and inject current, allow current to flow into the battery to recharge it at that precise voltage. So the more accurately we can do this, the better it is for the battery's longevity and service life. All batteries are different. There are different set points for different battery types: gel, sealed, flooded, even some nickel cadmium. And we take this into account when designing our set points within our controllers. And in fact, many of them, the Sunsaver MPPT, the TriStars, they all offer fully programmable and customizable set points to really fine-tune your battery voltage set points. You can also simply use the built-in settings, which are usually pretty good and cover about 90% of battery types. Again, all our controllers use that PWM type algorithm. Going on to the maximum power point type, these controllers are often the most sophisticated. As you've probably seen in the market, they vary widely in terms of cost and feature sets. We design our maximum power point tracker controllers to truly do just that. Harvest the maximum energy from your array when the sun is up. You never know when you're going to need the power, and we want to make sure we take full advantage of it as it's available. If you compromise on the type of maximum power point tracker controller you buy in terms of cost, you'll likely see a lower total energy harvest. It's very difficult to track the maximum power point of a solar array consistently throughout the day, accounting for changes in temperature and irradiance levels, and do so without losing available power. So the sophistication and the value in the controller itself is in the way that it physically tracks an array to bring the most power in through the controller and convert it down to battery voltage. This VMP of an array, all arrays are rated for a particular level. It varies. A 200-watt panel that might operate at a VMP under standard test conditions of, say, 37 volts might not quite operate at that level, that power level, in hot conditions. That whole curve, that performance curve, will actually shift down to the left, and you'll see a bit of a degradation in performance. That's just natural and due to the nature of the technology. In cold weather, it can shift up and in fact give you more power than maybe the nameplate rating on the controller, or rather on the panel. So the purpose of being able to understand and read that maximum power point as it changes throughout the day and do so accurately is critical to fully harvest the maximum amount of energy available from that panel. So you can see there's quite a few considerations. To just summarize real quickly between PWM and MPPT type controllers, when you're dealing with a PWM type system, the key to note is you really need to match the array voltage and the battery voltage nominally. So for, say, a 12-volt system, your off-grid panel should run about 17 volts, and you would size the system in amps. On the MPPT side, and the real value that this brings is you size it in watts, you can use a much wider range of available panels that produce all kinds of crazy voltages and convert down to a battery voltage of 12, 24, or 48 volts typically. And doing this allows you to take advantage of some of the lower cost grid tie type modules, 60 cell or 72 cell modules, and use that full amount of available power all day to provide maximum charging current to the battery. So while you do typically spend a bit more on the controller itself, in terms of the overall system cost, especially with panels being as inexpensive as they are these days, you really get tremendous value for your money, or for the homeowner's money as you're installing these systems for someone else, to provide as much energy as possible for lowest cost per watt. So again, as you're making the decision as to which charge controller to use, it's a fairly complicated decision. There's quite a few dimensions to evaluate in order to ensure you're choosing the right one. And to ignore many of these factors is to most likely compromise the optimization of the system in some way. Obviously, first you need to really look at what makes sense for your system. Do you need that extra bit of power from your panels that the MPPT can provide, or does a PWM type switching controller serve your needs? They both have their own type of application scenario. Again, environmental conditions. If you are installing a system in northern Canada on a cabin that will easily see minus 20, minus 30 C on a regular basis, you want to make sure your controller can handle that. If, again, on the flip side, typically at higher temperatures, it's difficult for power electronics to function well. And so looking at that, that last spec on the last page of the data sheet to really understand how the controller performs at various temperature ratings is pretty central to the decision. With Morningstar products, I can say that minus 40 to 60 C range is generally what you can expect. It might fluctuate a little on the higher end, but generally there is no need to derate your system to expect lower performance at those ends. The controller will function just as it's intended, just as it's rated throughout that whole temperature range, to push as much current as is available from the array into the battery. You might want to consider how your set points will be adjusted, or what's built into the controller. Gel, sealed, flooded batteries all have different general ranges of regulation set points. You might need to consider a low voltage set point that you'll dictate when your load will disconnect to prevent over discharge of the battery. It's important to know what the internal built-in settings are for a controller, and if the case warrants, whether or not you're able to go in and actually change those. With our SunSaver products, it's simple. You can either insert or remove just a small little select jumper to switch between a sealed or a flooded type battery. With a TriStar, ProStar, you get a few more choices. In fact, with a TriStar, there's actually 7 built-in pre-programmed charge algorithms, set points, and an 8th that's fully customizable. So if you have some kind of special battery type, or if you're doing a NiCad system, all that's fully programmable. Once you have the set points down, protections, as I mentioned, lightning is very important to consider what type of environment your controller will go into, whether or not moisture is a factor, whether you think it will be subject to any kind of variations in voltage for one reason or another. It's important to know that your off-grid controller will be operating when you go back to check on it. And these types of considerations absolutely have an impact on whether or not the controller will meet its expected service life. Depending on the application, communication could be a consideration. Many of our controllers have self-diagnostic capabilities to do the work for you. You don't have to troubleshoot and bring your voltmeter out to find out what might have happened in the system. easy to reset, easy to find information on the LEDs and flip through the meter displays. If you are in need of some of the more industrial type standards, we offer on the TriStar MPPT the full suite, the Ethernet, Modbus 485, RS-232 serial, and again the TCP/IP. So depending on your need for communication, our goal is to provide you with the open tools to interface directly with the controller at any level, whether you're an industrial type installer and you need to sync your TriStar device with other industrial equipment, you have Modbus. If you have no interest in getting into the last variable of your system, you just can use the meter. The idea is, no matter what your need, you can find the information you need and communicate directly with any Morningstar product to fit inside your system. Temperature compensation is one thing that I haven't mentioned so far that's incredibly important in system design and controller selection. Battery voltage, set points, and as you've seen earlier, panel performance characteristics change with temperature. It's probably the most significant variable in designing an off-grid system. You want to make sure your charge controller is able to compensate for those changes in necessary voltage set points on batteries. Many controllers offer this, some do not. All of our controllers offer at least a level of temperature compensation that's built in, standard 30 millivolts rather, per degree C. We offer temperature compensation terminals to run smaller gauge wire directly to a battery to gauge its true temperature and manage voltage around that proper set point. It can't be underestimated or overemphasized, the importance of making sure that your controller knows the true temperature of the battery and adjusts its set points accordingly. A cold battery will need to be charged at a higher voltage for the same amount of current than a warm battery. And without making this compensation, it's almost guaranteed that your battery will reduce its useful service life. To run through the last few, because I do want to have time to talk about our MPPT TrackStar technology and a few application scenarios. I'll try and get through this fairly quickly, but these all are important considerations. On the load side, LVD, you will want to ask the question, if you're running a DC load directly from your battery system, based on the sizing, it may be a good idea to have the option to cut off that load if the battery reaches a certain voltage. With our ProStar Sun Savers, it's built into the face of the product itself. With our TriStar, you can use it as an LVD type controller. You just need to place a separate controller in series with your load and your battery, and be able to monitor all this with some kind of a status indication. Both the array status, the battery status, and the load status. If you're not able to tell what's happening in your system easily at a quick glance, not only is it aggravating, but it really puts the system at risk. All of our controllers use a low self-consumption, especially as some of the controllers get bigger, more sophisticated, meters get brighter and bigger screens. Self-consumption is an issue. So you want to consider what is the self-consumption of a controller and how do they compare. You don't want useful energy poached from your system just to run the controller. At most, our TriStar, even with Ethernet enabled, will use about 2.7 watts. Not a bad trade-off for the value that it delivers. And consider quality. It's a little bit more difficult to quantify, but you can look at things like, what is the operating life of the controller? What's the mean time between failure? Was it manufactured in an ISO 9001 facility? What are its certifications? Does it have a warranty? Very important considerations. And also just simply ease of use. Can you put it put it in the system easily? Can you clearly understand how to wire it? Is there supporting documentation and tech support behind the product? And last but not least, the commercial side of the decision. You never want to go with a vendor that can't deliver, that doesn't have stock, that is hard to get a hold of. Morningstar obviously tries very hard and succeeds in doing these things well. Matrix always has stock of our product. If they don't, because you bought too much of it, it's in our warehouse waiting to be shipped in a day. When you call, you get a live body on the phone and direct access to our best design engineers and tech support on an ongoing basis. So hopefully this gives you a good idea of all the considerations that you need to make when choosing this central part of your system. There's a lot more detail we could go into, but I'll switch now to TrackStar and talk about our MPPT a bit, since this is so central to the solar industry today, especially in off-grid. Our TrackStar algorithm was patented, I believe, as the slide earlier said, back in 2007. It is a very fast sweeping voltage detection algorithm is the best way to describe it. It allows our controller to constantly manage the output of the controller according to an adjusted VMP on your solar array, and it does so very efficiently. This is an exceedingly difficult task to do. It involves, in our case, microprocessor control, some very detailed and well thought out algorithms that our engineers have spent quite a long time perfecting. And really the value at the end of the day for you is to ensure, to have the confidence that you can know your controller is not wasting power that could otherwise be used for the battery. It can't be underestimated, the importance of doing so, especially in off-grid systems. In terms of the efficiency, I'll show a few slides here in a minute. They all look like numbers, and I've heard it said before that efficiency is meaningless. Everybody tests under different conditions, and it doesn't matter. I would absolutely contest those assertions. It does matter. It's very important. And with the TriStar MPPT and the SunSaver MPPT operating well above 95, which is just typical for some controllers, you can be assured that most of the power, the vast majority of the power available for the roughly 5 hours or so a day you have, is harnessed. And I'll get into exactly kind of how we do this this magic in a bit more detail. I won't talk too much of the numbers here, but just a quick example to show what type of advantage you get with a 12-volt nominal off-grid type battery system. You can see the maximum power point in general runs for a nominally sized system at about the 17-volt range. If you're using a PWM system, your battery voltage will actually drag this down, and you'll lose the power between the roughly 14 or 15 volts your battery operates at and the potential the panel has at 17. With the maximum power point, we actually convert that power at 17 volts on the panel through a buck-type converter down to a 14.4, 14.5 volt battery regulation voltage. And what this does is it boosts the current available for charging, especially at times when, maybe in the morning there isn't quite as much charging current available, or later in the evening as the sun is going down. You can just be sure that the maximum power point is locked onto at all times of the day. One thing to note with our efficiency curves, we show here on the left our TriStar on a 48-volt system. On the right-hand side is just a generic, typical competitor's efficiency curve, which trails off at higher power levels. The way we achieve this is through kind of building 3 20-amp controllers, in the case of our TriStar 60, into one unit. And these different 3 stages turn on at various points in order to give you the most efficiency in that given power range. And these 3 stages are almost like gearing in a car. This is where you see these kind of funny-looking power curves that kind of plateau and taper off at higher power levels. So just some of the numbers you see, roughly between 97.5% and 99% for different VMP ranges. On the TriStar, you might see, for the same set of operating conditions on a competitor that doesn't have this 3-stage design, some reduced performance, back down around the 95% efficiency level that that is typical. And each percentage of this efficiency loss really translates into some significant power just kind of wasted. And we've done some rough calculations here and said that if you're running generally around 1,200 watts on your panel over the course of a day, even just 1% of efficiency difference can translate into about 100 watt hours that you're not being able to use in your battery. I mean, this could run a 50 watt light bulb for a couple hours. So it's in some of these more remote systems where every bit of autonomy, day of autonomy is really important. This is where efficiency comes into play. Again, to emphasize, with the MPPT technology, you get more power at earlier times of the day and significantly better efficiency in those lower output levels, and again at those extremes on the high end. They keep batteries generally at a higher state of charge than a PWM controller would even, and this translates to longer battery life. Every battery manufacturer will say that the higher state of charge you can keep the battery, the longer it will last. And to do so consistently with an MPPT type controller is probably the best thing you can do to make sure your batteries attain their longest level of system life. I think Sean, I might be running up on time, but I do want, if I could, just walk through a few application scenarios to put some context to all this.
Yeah, I think Kyle is, we're winding up to noon there. You understand that. So, but you've got some time. If you're some specifics, then let's get to them. There is one question. I don't know. We'll do it at the end, I guess. Denis Gignac has a question that we'll get to as soon as you think that's appropriate.
Okay, sure. Yeah, I'll just run through briefly a few of our more typical representations of where you see Morningstar products. Here on the left, this is a telecom installation down in Brazil, where they've actually used these small microwave backhaul type systems to provide communication for about 2,000 remote homes and villages around the Amazon basin. Clearly one of those environments that is pretty tough on power electronics, but again, that tropicalization, conformal coating, passively cooled heat dissipation design really comes into play. On the opposite end of the spectrum, this small, you can kind of see it in the middle here. I'll point to it. This is the panel, a weather station on the top of a mountain in Switzerland. I believe it's the Matterhorn. And this has been up there running for quite a few years without any attendance. It's a bit of a difficult site to get to. These are the kinds of systems that we try to perform well in. Again, in a marine environment or around lakes, you've got to deal with usually higher humidity levels, moisture, fog. On the upper right, rather the upper left, this is an installation, I think, in Perth, Australia. Really brutal, high temperatures, easily up in the 30, 40 degree C range during the day. Sea spray, salt spray, everything you can throw at the controller. Again, working very well. In the upper right, even some of the larger systems. I would guess this is somewhere in the 2 to 4 kilowatt range of power levels. You might see 1 or 2 TriStars or TriStar MPPTs handling that type of array. Right on the water, brutal conditions, heat, salt spray, very difficult to perform well in. Remote villages in Africa. Here's a couple. One in Kenya. The other, actually, I believe, is in Central Asia. TriStar products, SunSaver products, powering remote villages, pumping water, providing lighting that's otherwise impossible. So just some general ideas about how the products can be used. We'd like to see as many of your application photos as you're willing to share. Every little bit helps, and seeing the products and work at work, especially in some of the more extreme environments, desert, again tropical, really is a testament to our reliability. So I guess, Sean, if you have any questions, I'm happy to address them. That concludes the bulk of the presentation.
Thank you so much, Kyle. We do have it's a fairly specific question from Denis Gignac, and as soon as I can access it here, I'll share it with you.
Okay.
I may need, this is one of those things we talked about, Kyle. I may need some technical assistance here, and I'm sure Claudia will be here any second.
Well, I can also always answer any questions offline. Feel free to contact me directly. Put me in touch with anyone through either Patrick or Claudia or Sean.
You're gonna do it. Oh, sorry. Okay, so I can't access Denise' question, but I believe it was radio interference. If you could just speak to that, maybe specifically.
Okay. Yeah, this is a question we get quite a bit. The first thing I'd say is that on our MPPT controllers, radio interference is pretty rare. It uses a different topology in the system, a much higher frequency design. So at the radio frequency spectrum levels that are typical, we don't see much interference there. Where we have heard of some interference is coming from the PWM type controllers that switch at around the 300 hertz range. In some special cases, this can be right in that band where you might get some clipping or clicking rather in your overall system. That is a fixed frequency, but in many of our products it can be turned off, essentially. So you could change the product from a PWM type controller to an on-off controller, which greatly lowers that frequency from about 300 down to about 10. And most of the time we've found that this is, while it's not quite as good for battery charging, it solves the noise issue and still allows for a slower PWM type battery charging to take place. A lot of our products, the SunSaver MPPT, I know for sure has an FCC Class B type noise rating. Now, that's something that we've put some of our products through that we know are going to be used in potentially some industrial environments with noise. So look for that FCC rating as well, and with that you can be sure that it's one of the high frequency designs that is very unlikely to cause interference in the system.
Great, Kyle. Si vous avez d'autres questions, c'est le temps. If you have any more questions, please ask them now, as the webinar will soon be closing.